Hello everyone, and welcome. Today we're going to explore the fascinating world of ray optics. The title of our presentation is Ray Optics I. We'll be diving into the fundamental concepts, principles, and applications of ray optics. Over the next few slides, I'll guide you through the basics and help you understand how light behaves when it interacts with different surfaces and materials. Let's get started. Today, we're moving into the fascinating world of refraction at spherical surfaces, beginning with an introduction to the topic. We'll also explore the lens maker's formula later on, which is essential for understanding how lenses are designed and how they work. Let's start at the very beginning with the basic concept of refraction of light. Refraction is simply the bending of light as it passes from one medium to another with a different optical density. This bending occurs because the speed of light changes when it moves between materials like air and glass. Understanding this process is crucial because it's the foundation for how lenses form images. Whenever light encounters a spherical surface, like the surface of a lens, it bends in a predictable way. This leads us to the importance of the spherical surfaces themselves. They are key components in many optical devices because their shape influences how light rays converge or diverge. By studying refraction at spherical surfaces, we can better understand how to manipulate light to create clear images, which ties into the overall theme of optical design and the development of precise optical instruments. And as we proceed, the lens maker's formula will give us a powerful tool to calculate the exact curvature needed for lenses to achieve desired focusing properties. So, in essence, this introduction sets the stage for understanding how light interacts with spherical surfaces and how we can harness that knowledge in practical applications. Let's take a closer look at refraction of light. Refraction is the bending of light as it passes from one medium to another, like from air into water or glass. This bending occurs because light changes speed when it moves between materials with different densities. The key point here is that the amount of bending depends on the properties of the two media, specifically their refractive indices. This is why objects appear bent or distorted when viewed through a glass of water or a lens. Understanding refraction is fundamental because it explains many phenomena we see daily, like how a straw looks broken in a glass or how lenses work in glasses and cameras. It's a crucial concept that ties into the overall theme of how light behaves and interacts with different materials. In refraction, it's important to remember that the frequency and phase of light remain unchanged. What actually changes are the velocity and wavelength of the light as it passes from one medium to another. For example, when light moves from air into water, its speed decreases and the wavelength shortens, but the frequency stays the same. Now, the refractive index, denoted as mu, is higher for denser media compared to rarer media. So mu of a denser medium relative to a rarer one is always greater than 1, while mu of a rarer medium relative to a denser one is less than 1. For instance, the refractive index of air is approximately 1, which is the same as vacuum, meaning they don't significantly alter the speed of light. Optically, a rarer medium has a lower mu, and a denser medium has a higher mu. This difference in mu explains why light bends toward the normal when passing into a denser medium. Moving on to the laws of refraction, the second law, also known as Snell's law, states that for a particular pair of media and a specific wavelength of light, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. This constant depends on the media involved. The first law tells us that the incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. This helps us visualize how the light ray behaves when it hits the interface. Refraction can be simply defined as the change in the speed of light as it moves from one medium to another. And an important principle to remember is the reversibility of light. If you reverse the path of the light, it will follow the same path back, which is fundamental to understanding optical systems. So, in summary, refraction involves a change in the light's speed and wavelength, governed by the properties of the media, and it follows specific laws that help us predict how light will bend at interfaces. This knowledge is central to understanding many optical phenomena and devices. Let's take a closer look at the relationships involving the refractive index and the parameters mu and mu b first. Notice that a mu b is equal to 1 divided by b mu. This reciprocal relationship indicates a kind of symmetry between these parameters when considering different media. Next, observe that when you multiply a mu b by b mu, the result is 1. This simply confirms that these quantities are inverses of each other, which is a key point in understanding how light interacts with different materials. Now, moving on to the concept of the refractive index, which is central to understanding refraction through a compound slab. As light passes through multiple layers, each with its own properties, these relationships help us predict how the light will bend or slow down. This slide emphasizes the importance of these reciprocal relationships because they simplify the calculations and deepen our understanding of how light behaves in complex media. Recognizing these patterns is crucial as we explore how refraction works in layered or composite materials, which is a fundamental part of optical physics. Let's talk about the conditions for total internal reflection. First, the angle of incidence in the denser medium must be greater than the critical angle for the pair of media in contact. This means that the incident ray needs to hit the boundary at an angle larger than this critical angle to achieve total internal reflection. Additionally, it's important that the incident ray is in the optically denser medium. If these conditions are met, the light doesn't pass into the less dense medium, but instead reflects entirely back into the denser one. This phenomenon is known as total internal reflection, and it's a key concept in understanding how light behaves at boundaries between different media. It explains why, beyond a certain angle, all the light gets reflected back, which is fundamental in optical fibers and various other applications. Today, we're going to start exploring refraction at spherical surfaces, which is a fundamental concept in optics. On this slide, we'll introduce the basic ideas behind how light bends when it encounters spherical surfaces, like those found in lenses and curved mirrors. We'll discuss why understanding this refraction is crucial for designing optical systems that focus or direct light accurately. As we go through this, keep in mind that the principles we learn here are essential for understanding more complex optical behaviors later on. So, let's dive into how light interacts with these curved surfaces and why these interactions matter so much in practical applications. Let's go over some key points about the sign conventions we use in refraction at spherical surfaces. First, any distance measured along the direction of the incident ray is considered positive, while distances measured against it are taken as negative. This helps us keep track of the directions consistently. All these distances are measured from the pole of the refracting surface, which acts as our reference point. When we talk about the incident ray, we assume it travels from left to right, which simplifies our analysis and makes the sign conventions easier to apply. Now, moving on to the new Cartesian sign conventions, we generally consider the aperture, which is the diameter of the curved surface, to be small. This assumption allows us to work with small angles and simplifies the mathematics involved. Similarly, both the incident and the refracted rays are assumed to make small angles with the principal axis. This is crucial because it justifies the use of the small angle approximation, making calculations more manageable. Finally, when we refer to the object in this context, we usually consider it as a point object lying directly on the principal axis. This assumption helps us focus on the core principles without unnecessary complexity. All these conventions and assumptions are fundamental because they provide a consistent framework for analyzing refraction at spherical surfaces, tying into the broader theme of understanding how light behaves when passing through curved interfaces. Let's take a closer look at how refraction behaves when light passes from a rarer medium to a denser medium, specifically in relation to virtual images. When light travels from a less dense medium, like air, into a medium with a higher density, such as glass, it bends towards the normal. This bending can create a virtual image, which appears to be on the same side as the object, but is actually formed by the apparent divergence of light rays. Now, focusing on the surfaces involved, a concave surface typically produces virtual images when the object is placed within a certain distance from the surface. The key point here is that the virtual image appears to be located behind the mirror or surface, due to the way the rays seem to diverge after refraction. Switching gears, when light moves from a denser medium back into a rarer medium, like from glass to air, it can produce a real image. This occurs because the refracted rays actually converge at a point, forming an image that can be projected onto a screen. And when we talk about refraction at convex and concave surfaces, these are fundamental in understanding how images are formed. Convex surfaces tend to produce virtual images when the object is close, and real images when the object is farther away, depending on the position. Concave surfaces can produce either real or virtual images, based on the object's placement relative to the surface. All of these concepts connect back to the overall theme of how light behaves when it encounters different surfaces and mediums, shaping the images we observe in various optical devices. Let's take a closer look at the lens maker's formula. This formula is fundamental in understanding how lenses focus light and how their shape and material influence their focusing power. Essentially, it relates the focal length of a lens to the radii of curvature of its two surfaces and the refractive index of the material. By knowing these parameters, we can predict how a lens will bend light and where the image will form. This is crucial when designing lenses for cameras, microscopes, or eyeglasses, ensuring they produce clear and sharp images. The key takeaway here is that the lens maker's formula provides a direct link between the physical shape of a lens and its optical performance, helping us optimize lens design for various applications. Connecting this to our overall theme, understanding this formula allows us to manipulate lens parameters to achieve desired imaging qualities effectively. Let's talk about the principal axis of a lens and the key points related to the focal points. The second principal focus is the point on the principal axis where an image is formed when the object is placed at infinity. In other words, if you imagine an object infinitely far away, the rays coming from it are essentially parallel, and they converge at this focus after passing through the lens. Now, the first principal focus is a bit different. It is the point on the principal axis where, if you place an object, the image would be formed at infinity. This means that the rays from this object are directed parallel after passing through the lens, and they appear to originate from this focus. Both these points, the first and second principal focuses, are crucial because they help us understand how lenses form images depending on where the object is placed. They are essentially the two key points that define the behavior of converging and diverging rays in lens optics. Recognizing these points helps us predict how images will form and where they'll appear relative to the lens. Now let's take a closer look at the lens maker's formula. This formula is really fundamental because it connects the radii of curvature of a lens to its refractive index and its focal length. Essentially, it helps us understand how the shape and material of a lens influence its focusing power. When we're dealing with a convex lens, the formula allows us to see how changing the curvature or the material affects the focal length. It's like a bridge between the physical shape of the lens and its optical behavior. Moving on to the thin lens equation, often called the Gaussian form, this is the key equation for analyzing image formation in thin lenses. It relates the object distance, the image distance, and the focal length in a simple, elegant way. Understanding this equation is crucial because it helps us predict where the image will form, whether it's real or virtual, and how sharp it will be. Connecting this to the overall theme, these formulas and equations give us powerful tools to design and analyze optical systems, whether it's for glasses, cameras, or microscopes. They are fundamental to mastering how lenses work in real-world applications. Linear magnification produced by a lens is defined as the ratio of the size of the image to the size of the object. Essentially, it tells us how much larger or smaller the image appears compared to the actual object. This is a key concept because it helps us understand the extent of magnification that a lens can provide. When the linear magnification is greater than 1, the image is larger than the object, which is common in magnifying glasses or microscopes. Conversely, if it's less than 1, the image is smaller, like in a camera lens or a projector. Remember, this ratio is a simple yet powerful way to quantify the magnification effect of a lens, tying back to our overall discussion of how optical devices manipulate light to produce images. Now, as we wrap up the topic of ray optics, I want to highlight an important concept about the power of a lens. Essentially, the power of a lens describes how effectively it can bend or refract light that passes through it. Think of it as a measure of how strong the lens is in terms of focusing or diverging light rays. This power is actually the reciprocal of its focal length, meaning if you know the focal length, you can easily find the power and vice versa. When we measure focal length in meters, the lens's power is expressed in diopters, abbreviated as D. So, in simple terms, the greater the power in diopters, the more strongly the lens bends light. This concept ties everything we've learned about how lenses manipulate light rays, and it's fundamental in designing optical devices like glasses, microscopes, and cameras. Understanding this relationship helps us grasp how different lenses serve different purposes in optics.